Alright, today we'll be going over the low pressure sodium lamp and the type of light it creates along with its technology. Next we'll be expanding 4 times 4 into a very large equation. And after that, we will be solving an integral using partial fractions. You cannot see that whole thing, don't worry, I'm aware of that. Still getting new to this whiteboard stuff. Anyways, yes. And it'll tie in the next video, which will be using a new method of calculations that you guys have to sit and wait for. And after that, we'll be using a new method of calculations to be able to tie it to this integral in the next video. Hello, welcome back to my channel. I'm sorry for the little bit of an upload delay. It's because I've gone back into school and I no longer have a ton of free time on my hands. But yeah, that's that. Today, we will be doing something a little differently. We will not be confining ourselves to the world of mathematics, but be introducing ourselves to more real-life things and then somehow incorporate that into what we're doing currently. So, to begin, I'd like to show you a little something of mine. Right here, it is a very special type of light bulb. It is a type of sodium vapor lamp, very close to fluorescence, called a low pressure sodium light bulb. And for those who do not know, these are very special because they make strictly monochromatic lighting at a wavelength of approximately 589 nanometers. And yeah, as you can see, it's right here. And yeah, so low pressure sodium bulbs, they're very obsolete compared to LEDs. However, it wasn't until like a couple years ago that LEDs were able to beat these in efficiency, because these are like ever since it was first created, was the most efficient type of lighting technology known. And so, but they were used in Europe because that's mainly where they were used. However, over where I live, and yes, I know I'm about to dox myself when I say this, they use them in streetlights, similar to Europe, because places where there are observatories, they use them because the monochromatic light can be easily filtered out, as you may probably already know. But there was a thing with LEDs where there was like a specific, I don't know how to explain it, but there was a way to filter out LEDs by refreshing exactly staggered from the refresh rate of LEDs, because every single type of light, except for incandescent types of lights, flicker at a varying frequency, like 60 hertz or 20 hertz, because every single light, except for incandescent lights, need a type of ballasting or other electrical equipment in order for them to work. Which is why if you've ever been in a room and you record, you can see those darker, whiter bands called bar flicker. Yeah, so they can just refresh when the lights are flickering, so you won't be able to see any of that. Anyways, so first thing before we get started is let's do a little bit of stuff with this low pressure sodium bulb. Number one, let's colorblind myself. So yeah, I'm gonna stare at the bulb for about 3 hours and see what happens. Alright, so the type of thing I bought this light bulb in was a safe light, because it was about the cheapest thing I can buy with all the electrical equipment. So it's not really meant to produce a lot of light, it's actually meant to dim a lot of the light. But I'm just going in and put the bulb in real quick. This is a super old porcelain socket. It's the bulb did not want to come out at first. Alright, let's get the wire to hold it up. Alright, let's plug it in. Alright, so now you're going to see the neon discharge come on. I think it's quite the hum. I don't know if you can hear that, but the whole thing is vibrating. well, that's what you get for magnetic ballasts. Yeah, so the way that these work is that neon, they use this neon as a starter gas to heat up the sodium inside the arc tube, and then the sodium begins to ionize, which lets off that yellow light that everyone knows. So yeah. Also, so that's why the bulbs take time to light up. So like if you've ever seen one, got a glimpse of them when they're warming up, they'll look a little red. This is why, it's because of neon. So yeah, we're gonna let this warm up, and I'm probably gonna do something to entertain myself at the time. Bulb itself, it looks a bit more red. I'm gonna try and fix that actually right now. Well, we won't be going colorblind. I can tell you a little bit of other cool stuff about this light, I guess. Can't tell colors, I guess. Like, look at this piece of bread. Does this look like a piece of bread? Of course it does. What about this bowl? What color is this bowl? Yeah. Alright guys, welcome back to the chalkboard, and I'm sorry if there are any light leaks, because I really have my thing right here. So, let's go a little crash course on how lighting works and how this bulb works. So, let's say, alright guys, say this is our bulb right here. So, this emits a wavelength of 589 nanometers. Alright, and let's say we have an object in a circle, or an oval, I guess, which has when light comes, it, let's say there's just like a sun right here, it emits wavelengths of the entire spectrum, including the invisible spectrum, obviously. And so whatever color this color is, say red, it'll reflect, it'll absorb every single color in the spectrum that this emits, except for red, which is what it'll bounce back and reach your eyes, therefore making the circle appear to be red. However, if let's say we do not have another light source, and we only have this, the low pressure sodium bulb, and it emits a wavelength of only 589 nanometers, and this is still red. This is the same way. Depending on how far away from the spectrum is, like let's say we have a color wheel, blah 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 blah. This could be like 589 right here. Directly on the other side will be like some other color, possibly close to like the opposite of yellow, which blue, yeah, blue. And so let's say the circle is blue, it is going to absorb pretty much all of the wavelengths, making it appear to be black. Let's see if I have a blue object that I can grab. Oh, this is old painting that I made probably like 5 years ago. So this is Minecraft slide, I made it some time ago. And so this is a blue sky, but it appears to be pretty black, and that's because it is absorbing almost all the wavelengths right here. But let's say we have something that is red. It is only, depending on how close it is, will be like, I don't know, like right here or something. And so it's pretty close to 589 meters. It is going to reflect some of this out, making it appear to be a bit more yellow. Here, as an example, this red string that I have, you can see that it is reflecting some of the wavelengths right here, as you can see. So, also, please do not take this as a professional thing. I do not know how color works that well, but yeah. So that is why you are colorblind, or at least you cannot discern color when this is the only source of illumination, and that is because of this, what I just described. Actually, I'll provide an example real quick as to what happens if there's like a light leak from my window right here. So this is like a green little cloth, and if I open this up, you can suddenly see how it's slightly green, twilight, and a shadow walks out of it. Yes,
obviously if there's another light switches on that, you'll be able to see colors of the light. So yes, 589 nanometers, shape set only. Yeah. Let's just focus on the number 589, alright? So, let's say we have a circle right here. S squared plus y squared equals r squared. And let's say 589 is the radius of the circle where r is equal to the radius. So this will give you something like that, a little circle, with this length being 589. Alright, so let's convert that into a function. So we have y is equal to negative x squared plus r squared all over rooted. Yes, I'm pretty sure. Take two. Alright, let's see if we can make this into a function. So, squared squared, square root of that, and that y is equal to square root of x plus r squared. Alright, that's the function, which will be something like this. Alright, so let's try to integrate this part. We're not going to use this type of integral that I did, but this is a real integral, where we will get pi radius squared. Alright, so this integral does include trigonometric substitution, which makes integral quite challenging. However, there's a video that I'll link in the description that if you want to have a better grasp of it than what I'm going to give you, because I'm just going to time-lapse it, it'll be down below where you all know it is. Alright, so back to the integral. So my geometry teacher said that their work teaches me calc. This is an incredibly difficult integral to do. Don't worry, your homeboy's got this. So let's take the integral from 0 to r, and we have to multiply by 4 since we're taking only a fourth of the circle. And then we have this, x squared plus r squared dx, right? Do this. X is equal to r sine theta, right? And dx is equal to r cosine theta, because the derivative of sine is cosine. Everyone knows that. Alright, so let's get to the substitution. Oh, and yes, if we are integrating with respect to theta. If we're integrating with respect to theta, we have to push r to pi over 2 radians to signify 90 degrees, because it's going 90 degrees that way. Does that make sense? Alright. Alright, so there you have the integral. To be fair, I mostly refer to my notes because I integrated it one time in class. I've done this integral a couple times. It's good to memorize these trig substitutions. Actually, my house has cos squared theta. So yeah, so here's how you get pi over d squared. And we know that 589 is equal to r, so we get pi 589 squared. And boom, there we go. So we went from this to that. And there we go. So now that we know everything about circles, trigonometry, lighting, and certain matters, we are going to dive into electronics now. It's actually quite basic. So let's go. Alright, so let's do some. So we have our power supply right here, and we have two wires coming out of it right here. There's a cold, and there's a hot, and then there's an optional ground wire. So let's say we have a fixture right here. The ground, and let's assume we have a metal. The ground is going to be connected to the metal. Obviously it's called grounding, and thing feels like a bit of metal. And then there's going to be the cold, which has a ballast. This will be showing about each ballast, obviously. So it has a ballast, and there's two spots for it. So there's the cold that's going to go into this part, and then there's going to be a switch right here. In order to turn the lamp on and off. This one does not have a switch, it's just when you plug it in, it turns on. So yeah, so this is optional, and then it's just going to go straight into the hot version of the ballast. And then the ballast comes, just ignore how this is kind of sloppy, this is just to mention how the other picture. So then there's a socket right here, where the bulb slips in. Right here. And so the ballast is going to output this, and there's going to be two spots for it. So the hot is going to go into the hot, and the cold is going to go into the cold, which is connected to the ponds on here to connect the base, and boom, light. And so yes, it's really quite that simple. Sometimes you're gonna have some capacitors in your blah blah blah, but I don't know enough about electronics for that. So yeah, and the ballast essentially is a magnetic ballast. The way that it works is that inside the ballast, I was actually wrong with the capacitor here. The capacitor is in the ballast, so there's a big capacitor right here. That's probably like in that little spot. So obviously smooth the current, and there's a choke right here, which is just like a coil, an electromagnet, and then there is a transformer. And there's a transformer right there, and that converts the wattage of whatever this is coming in, like let's say 120 volts, or this one works at 170 volts. I don't know, I'm not very smart at how everything works, but this could either convert 120 volts into 35 watts, something like that, because, or whatever this bulb operates on. I believe this is a 35 watt bulb. So yeah, so we have the capacitor, which moves the current, into the choke, which limits the current, which is probably what converts the 120 volts to 35 watts now that I think about it. And then there's a transformer. I don't know if you actually need a transformer. I'm assuming if you're dealing with like incredibly high powered lamps or something, you could have a transformer. But let's just say, I don't know, anyone who actually knows how electricity works is probably deeply fuming right now. I'm sorry, I did 6 minutes of research for this. Use that as a coil. And so, the reason why these vibrate is because when electricity passes through it, it causes it to contract a little bit, like the ballast or the iron or whatever. That's what it's on. It causes it to contract, and I believe that the hertz outputted or inputted technically into this ballast causes it to vibrate. And let's say this is vibrating at 50 hertz because that's what a low pressure circuit bulb can act at 50, 60 hertz, but I'm going to use 50. So it is 50 hertz, which is getting put into here, which is causing the ballast to vibrate at 50 hertz, which causes a sound wave operating at probably not 50 hertz, now that I think about it, because it sounds super deep. But yeah, it causes sound waves happening based on the vibration, and then that reaches our ears, and then that's why it hums. Simple. Alright, back at it again with the math stuff. Don't worry about this, we'll get back to low pressure sodium, but for now, we're going to do a little bit of math. Go on my papers. Alright, so as you may know, is somewhere in our master equation. It's like the square root of 4 times 4 over 10 plus that, all like over some number. But right now we're just gonna focus on 4 times 4. I swear math is haunted, bro. Alright. So, I promise you this will not get as extensive as 2 plus 2. It will get a little extensive, however, it'll pale in comparison to 2 plus 2. So, let's get working.
Alright, so that concludes this rendition of 2 plus 2 the hard way. I hope you found the video entertaining, and I am sorry how we were not able to dive any deeper into low pressure sodium. However, I will be able to tie it to my equation somehow in the future, hopefully near future, and as a little teaser for the next video, just so I can keep you on your feet, I will be going over a method. It's kind of hard to explain, where you can have any number, let's just say like 10, and then you can make it equal to the integral with 0 to a f t, or to literally any function you can plug into here. You can plug in the functions that I was doing earlier in the time lapse. You can plug in anything, and all it depends on is a. And in the method that I found, you'll be able to find a to plug into this function to be able to equal to 10 any function. You can get a, because like when you do this, let's just say like we have ln of x as our thing, and then you do this, integral ln of x is 1 over x. Wait, no, it's the other way around. 1 over x is ln of x. Ln of x. And so the way you parameterize a function is 0 to a, and so then you plug in a for x. So that's what you mean, and then that can be equal to 10. So yes, I found a way to do that. You probably already know how to do it, and I thought it was kind of cool for me. So anyways, yes, I hope you enjoyed watching, and trust me that this will be the first thing I go over in the first video. Alright. See you later.